In the last video, when we were looking at non-uniform circular motion, I pointed out that there was no rotation without deformation. And this actually gives us a good segue into what are called fictitious forces. And you'll notice I put quotation marks around the word forces. And that's because in a Newtonian framework, they aren't even forces. But we'll get into that. Honestly, this is something that gets brought up at least a little bit in pretty much every introductory physics book. And I really wish that they wouldn't bring it up because I think it creates more confusion than it helps. It is certainly appropriate in more advanced treatments, say a 300 or 400 level advanced undergraduate course would be a good example of that. But I don't think that this is really super helpful at the introductory level. That being said, since every book brings it up, I find it necessary to talk about it a bit more so that we understand what it is the books are trying to bring up when they're discussing this, so that we can then kind of put that off to one side and not think about it again. So let's take a bird's eye view of a curve around a road. And let's say you are in a car. So we're looking down from above here. Car's going around the corner like so. And here you are in the driver's seat of the car. Now, my question for you is, what is it that's making you go around the curve? Because after all, by Newton's first law of motion, the way you want to go, and I'll put want in quotation marks here, just saying this is what Newton's first law says is the natural state of affairs, is to go in a straight line at a constant speed forever. But you, personally, sitting in the driver's seat, are going around the corner along with the car. So let me ask you, what's making you go around the corner? Okay. The answer is, it turns out, is a combination of forces of friction from your seat, combined with normal forces from the side bolsters on the seat, combined with normal forces from your lap belt that you're wearing as you're driving your car. Now, this is going to stress my artwork to its absolute limit, but we can use this to think about what this is going to do to your butt. So, here's the seat, and this is the side bolster here. And I am just going to try to draw some hip bones and a spine. And this is not going to go well. Let me move that. Oops. There. Yeah, up there. That'll do. So those are some hip bones. And we're going to draw the beginnings of a spine. So yeah, just use your lots and lots of imagination here. So hip bones, hip bone, and this is some of your spine right here. Now what's happening is the side bolsters here are exerting normal forces onto your spine. So if, say, let's say going from this view here where we're turning to the left, if you're turning to the left, what will wind up happening is especially this hip bolster right here will be providing a normal force to help your hip move around the center. And then while we're at it, your lap belt So I'll try to draw in a lap belt here as well, and this is really not going to work out well. There, that's the lap belt. So the lap belt is also providing a normal force. So this is from the lap belt. And this is from the side bolster. And also, we will be having a force of static friction from the seat as well. All of these are directed towards the center of curvature. So this is our plus R direction. All right, so all of that combined is what's moving your hips around the same curve that your car is going around. Well, that's good, but what's moving your head? Pause and let's get back to that. Okay, so what's moving your head is actually your spine and the muscles attached to the spine. The one thing I definitely am not is any sort of an anatomist, as you can probably guess here. So apologies to those of you who know far more medicine than I do. But let me draw your spine. So here's the deal. By Newton's first law of motion, so this is your head. Yeah, I know. And I'm trying to draw a few vertebrae of your spine. But by Newton's first law of motion, what's happening is your head also wants to go in a straight line at constant speed. So it would be wanting to go straight up in the t direction, in the plus t direction here. And so as your hips are curving around like so, your head keeps moving forward. This causes there to be a bit of a curve into your spine. Now, the seat will also have side bolsters on the back, which will be pushing on the shoulder blades. That's part of it too. But I was interested specifically in your head, just because for visibility reasons, you usually can't make the bolsters go all the way up to your head. So what happens here is, because this is being leaned over the side, all the little tendons and interstitial muscles and everything like that are effectively exerting a tension force on your head like so. And part of that will be in the radial direction, and that is what is going to make your head follow the same path as your hips. And you can see this in race car drivers. If you take a look at photos of race car drivers, one of the things you'll notice is that those people have some serious neck muscles. In fact, they do weight training specifically to help make their neck muscles bigger. And this is because as they go around the corners at extremely high speeds, their neck muscles are what make their head go around. Now, this turns out to actually potentially create long-term damage, especially since attached to the head is a crash helmet that weighs quite a bit itself. So the race car drivers now usually have a system called HANS, which stands for Head and Neck System, where basically they wear a special collection of braces that sort of creates some artificial tendons that attach between the brace that connects the shoulders and the helmet in order to take some of the stress off the real tendons and the real muscles in the neck. But let's think about what's happening here. So this is a case of no rotation without deformation. The spine got curved off to the side, and the length between each of these things increases. So as you drive around the corner, you feel like your head is being thrown to the outside of the curve. Now, this sensation to you feels for all the world like a force. And this is where the fictitious forces come in. So what's really going on is Newton's first law of motion is saying that your head wants to go in a straight line at a constant speed. But since your seat has other things to say about what's happening with your hips, your spine gets tilted to the side and stretched out, making it feel to your nervous system like your head is being thrown to the outside of the curve. Now, since you're sitting in the car, it's natural for you to pretend that you're not being accelerated, but that's not really true. After all, you're going around this circle you're going around at a constant speed, but in order to change direction, you have to have an acceleration pointed to the center. So, in the Newtonian framework, this makes you an accelerated observer. So this means you are not an inertial observer. And so Newton would say that you're not eligible, quote unquote, to do physics calculations. So you'd have to imagine instead what some person by the side of the road would say is happening, and they would say, oh yeah, your spine is getting tilted over to the side and it's getting lengthened out, and because of that, you get this radial component due to tension in the spine that's accelerating your head to match how your car is accelerating. Now, there are non-Newtonian frameworks that you can have, and this is where the idea of fictitious forces comes in. There is a physicist by the name of D'Alembert who said, why shouldn't you be able to do physics? And by that perspective, D'Alembert found that, yeah, you could build a framework where you could do mechanics, but at the cost of adding potentially up to 4 fictitious forces. TIOUS forces. For those of you keeping score at home, they are the inertial force, the transverse force, the centrifugal force, and the Coriolis force. In this example here, if you are going, so here's where you're pretending, this effectively is you're pretending that your frame isn't accelerated. And so in this framework, for this case here, if you want to pretend you're not being accelerated, you've quit doing Newtonian physics, which is our focus here in these videos, and instead you've switched over to D'Alembert's viewpoint. And D'Alembert would then say that you have to create another force, which in this case would be the centrifugal force, that you would swear is what is trying to throw your head out of the car. Now, this force, for our purposes, this force has no actual physical reality. These are corrections that you do because you're pretending that your frame isn't accelerated. Your reference frame really is accelerated. And you can tell that, for instance, because as you drive around a corner, you can see, say, your parking lot tag tilt over to the side. And you know gravity should be pulling it straight down. Since you see it tilting over to the side, that tells you you're in an accelerated frame. But computationally, you can go ahead and pretend that you're not in an accelerated frame, but the penalty for doing that is that you might have to add up to 4 of these fictitious forces purely as a mathematical correction to the fact that you want to do physics in a frame that Newton says that you shouldn't be able to do it. And there are practical uses for that. For instance, we live on a rotating Earth. So that means we are all accelerating towards the Earth's rotational axis. A lot of times we would like to pretend that that's not the case. And so it would be computationally convenient for us. If needed, we can correct for the fact that we're pretending the Earth isn't rotating by adding these fictitious forces. But for our purposes here, they are mathematical figments that exist purely to correct for pretending that the accelerated frame you're in isn't really accelerated. So as far as I'm concerned, for everything that we're doing in the rest of this entire video series, we're going to be working in the Newtonian framework. And so if you find yourself looking at an accelerated frame, what you need to do is think about an observer who isn't accelerated and analyze everything from their perspective. And so as far as I'm concerned, for the rest of these videos, there is no such thing as a centrifugal force, a Coriolis force, a transverse force, or an inertial force. So that's my rant about fictitious forces. Hopefully it gives you a little more background of what it is that introductory textbooks are trying to talk about when they bring it up. Again, like I say, I really wish they wouldn't even bother bringing it up, because I think we just need to focus on the Newtonian framework. So if you're analyzing a situation like this, the observer that you should pick is the person standing by the side of the road who says both the car and you and your hips and your head and everything else are being accelerated toward the center. Let them do the physical analysis for the situation. Alrighty. So believe it or not, going forward, we're not really introducing any new laws of nature. We will be instead transitioning to other computational tools that will make what we have already easier to apply in certain circumstances. So in the next couple of videos, we will be picking up with impulse and momentum. We'll see you over there.